Thank you for inviting me to share our latest results on assessing geohazards of the Banda Islands and trying to reduce the risk of those hazards. I will discuss the three major geohazards that most threaten the Banda Islands and also eastern Indonesia. I would like to acknowledge all of those who have helped, the shoulders that I'm standing upon, the people who have gone before and the people who are working now from a number of different institutions, and especially the people at the local level. These different organizations collaborate under the direction of a nonprofit I founded called In Harm's Way. And the mission of In Harm's Way is to foster collaboration in end-to-end natural hazard risk reduction. So let's start by talking about the tectonic setting of the Banda Arc. As you can see here, this is the Suna Trench turned into the Timor Trough. So what's being subducted here is the Australian passive continental margin. And that subduction is causing a collision between the arc and the continent. You can see the arc is extinguished here. And you can see how in the forearc region there's lots of accreted material from the Australian margin. But the Banda volcano itself is quite unique, mainly because of its size. The volcanic complex here is 110 kilometers wide. And the latest eruption was in 1988, but the latest activity was in 2017 when we had seismic clusters. So let's start with talking about the volcano hazards. Again, here is the size, Google Earth profile through the Banda volcanic complex, and you can see it rises from the adjacent seafloor for over 5,000 meters up to a height of around 300 meters above sea level. So what we're seeing here on the surface above the ocean is just the very tiny tip of one part of this enormous volcano. The explosive potential of this volcano is really not known, but if volcano size correlates with explosive power, like in places like Toba and Tambora, this is the size of Tambora. This is the size of Toba and 3 times the size of Tambora, which could not only affect the Banda Islands themselves, especially those that are inhabited, but also cause a global climate change. This picture from Wikipedia I'm showing so I could draw your attention to the fact that we discovered in 2012 a normal fault that cuts through the summit. You can see there's this fault scarp right there on the summit, and then its geometry curves downward, meaning that all of this area to the west side of the volcano appears to be unstable. One of the evidences of that is in the 1988 eruption, the lava didn't flow out of the summit, but it found this normal fault and flowed out of the normal fault on both sides of the volcano. Let me just take you on a quick tour of the Banda Islands. You can see here, this is the innermost caldera right here, and this is the outer caldera right there, and we think there's actually another one that's even further out, showing that there's been some huge explosive eruptions in the past. As we pan to the south, you can see the summit here has these craters from previous eruptions. And then you see this thing right here, which is the fault scarp of a big normal fault. Actually, more than just one scarp, and there's steam pumping out of this fault scarp, meaning that it's deep-seated. It goes down far enough. We don't know exactly how far it goes, but at least far enough to tap in to the heat. Another view of this from Google Earth shows the lava flows from the 1988 eruption coming out of the sides. So we've mapped the normal fault scarp here on the surface that goes through the summit, which I just showed you, but then it also continues in both directions. Based on that, we speculated that it's possible that this entire area outlined in yellow dots here could slide. And that area is represented here in this red part of the volcano. Let's take another view from another video of the previous landslide that occurred. This is the landslide scar that occurred before, probably during the 1988 eruption. You don't see any steam coming from the crater, but you do see it right there. You do see it coming out of the normal fault scar. And you can see the summit here was cut by that landslide. Well, we think that same thing is happening again. Here's a photo of the landslide scar. You can see it here in black. And what we need to do is make sure we have a way to measure periodically if the distance between this part of the volcano and this part of the volcano is changing, and if so, how and how much. The best way to be able to be warned that the instability might be becoming worse is to have continuous GPS recording stations on here, so that if it started to move faster than normal, we would have a way to warn those in harm's way and get them out of the way. Because once this landslide actually occurs, the amount of time to do that is too limited. Here's some other photos of the landslide scar. You can see it's dipping this way, inclined to the west. In some places, it's actually turned more into a tension fracture or a rift zone, and is extruding steam. Let's talk now about the tsunami hazards of having a slide or a sector collapse from Banda Api. Let me show you the animations from the numerical modeling that we did of the collapse of this area right here, the western part of Banda Api. You can see the part that we've used for the collapse here. And if we look at it in cross section, you can see this goes into the water is pushed, comes back, and it makes a very large positive wave that then completely covers Palau Ai and mostly covers Palau Run. I'm going to show it again so that you can see what the time is like. For example, right there, we've only been running the model for 2 minutes and 30 seconds, which is the time it takes for the wave to get from Banda Api to Palau Ai, and then to Palau Run for almost 5 minutes. We need to monitor this so that we can warn the people in advance when we think that there's changes in the motion of that volcano. And if it starts to erupt, these islands should be evacuated. In fact, the whole area should be evacuated, because the tsunami of the sector collapse is not only going to affect these islands, but also, as you can see as we continue the animation, the rebound comes into the strait here between Banda Besar and Banda Nira. Let's look at these animations also from the model. This is looking to the east, and you can see what happens as the wave propagates towards these islands. You can see that it does inundate much of the area, especially the coastal plains where most people on the Banda Islands live. Here's looking towards the west of the same phenomenon. And you can see what happens here as this wave comes in from both directions and starts to cover the area that's mostly inhabited. To summarize, you can see wave heights of 75 meters here that hit I, and 45 meters that hit Rune. And where Banda Neira is, you can see at least 20-meter waves, 30-meter waves here in Banda Besar. We used Google Earth to identify all the buildings that inhabit this area. And you can see in red, these are the buildings that are going to be inundated by the tsunami in Banda Neira, Banda Besar. The blue are buildings above the wave height. But you can see that every single building on I and only a few buildings on Rune would survive. Nothing would survive here. And this shows, the number of buildings that we were able to count, what the population distribution is, and using that to say that the percentage of buildings affected on Banda Neira are almost 70%, 100% on I. On Rune, 70% again. On Banda Besar, about 50%. So it's overall around 60%. The number of individuals affected is also going to be over 10,000. What about tsunamis that don't come from the volcano but come from other sources that hit the Banda Islands? In our querying of historical records, we found that there was a huge tsunami in 1629, which we have modeled, that came from the area around the eastern part of Suram. The 1852 megathrust earthquake also caused a tsunami that overcame Banda Neira, and in 1841, the same thing. We've also modeled the 1852 event. So here's the 1852 event. You can see these red dots here are places where we call human seismometers. People, mostly Dutch colonists, identified the wave height and also the amount of time it took for the tsunami to arrive after the ground shaking started. With those two bits of data, we are able to then reconstruct from the wave heights the magnitude of the earthquake that caused it, and from the time delay between the shaking starting and the arrival of the tsunami, we can determine the distance. And we've done this in an ad hoc way and found, that it has to happen somewhere in this subduction zone. There's no other subduction zone that could create a big enough tsunami to go all the way to where all of those red dots are. So we used a Bayesian analysis, which means that we chose a prior. We asked our supercomputer to search within this area right here. And what the supercomputer does is what's called a random walk. It randomly starts a dot here, and the dot starts to move randomly until it continues in a direction of higher probability. And then it stops. And you can see that almost all of them stopped right here. There's no way these areas here could have caused what we observed on all those red dots right there. And the only place where there could have been a volcano, a large earthquake that caused those would be if its epicenter was right here, south of the island of Suram, and not very far away from the Banda Islands, which are right here. This was back in 1852. And since then, enough elastic strain has accumulated along that subduction zone to create a similar event. We have made a tsunami model of this. These are the control points right here. In this case, this was before we did the Bayesian analysis, so we put the earthquake there. You can see the negative wave going, and then these are the positive waves. You can see how much slower the wave moves where the water is shallow and how much faster it moves where it's deep. But look at how many times the Banda Islands become overcome by waves. So the first wave arrives within 15 to 20 minutes of the earthquake. Water goes out, and then the positive waves come in. You can also see that these waves affect a large part of eastern Indonesia, not just the Banda Islands. So let's talk about earthquake hazards then. These arrows here show two different types of measurements of how the plates are moving in the eastern Indonesia region. The blue is what's predicted, the red is what's measured from high-resolution GPS surveys. You can see that the Australian plate is converging to the northeast at a rate of about 7 centimeters a year. And since there since there are no historical records of any megathrust earthquakes and tsunamis on the south coast of Java and Bali and these other islands all the way to Sumba, that means that at 7 centimeters a year over 500 years, that's 35 meters of elastic strain energy, which is accumulated, which means when that is released, the island of Java will jut to the south about 35 meters, close to the speed of sound. And that motion creates a huge tsunami. The same is true with the collision zone here. The velocity is less because the strain is distributed, but still over 500 years, that's 15 meters, which could produce an 8.4 earthquake. The area right here, which caused the 1629 tsunami and earthquake in Banda, the 1629 earthquake transformed the Banda Islands into a rubble heap, according to the historical records, could have an earthquake right now of at least 8.8, and the same to the north, an earthquake right now of 8.7. I don't know of any other place on the planet which is surrounded by so much strain accumulation. The earthquakes in these areas over the past 100 years have in no way taken up the motion that's been stored. So this is a warning to this whole part of eastern Indonesia, especially Java, that these earthquakes are going to happen. If they happened right now, this one would be a 9, this one would be an 8.4, an 8.8, 8.7. The longer it waits, the larger they will get. We need to build our infrastructure with this in mind. Historical accounts of damaging earthquakes on the Banda Islands is another interesting story. There's been 20 damaging earthquakes from 1618 to 1859. And 5 different times, those earthquakes transformed the islands into rubble heap, where almost all the buildings were destroyed. The bad news is that since 1859, there has not been a damaging earthquake on the Banda Islands, which means that during that time, we have been building up elastic strain energy. And when that is released, it will cause a large event. One of the most important things to take into account when we have this kind of seismic risk is in which way is the ground going to shake, because all ground is not the same. For example, in zone A here, or site A, you can see that this is mostly bedrock. And you can also see that it it has a steeper slope, which means that there's erosion happening here, not deposition. Well, right next to this, you have an area of deposition right here. So the bedrock here is much more consolidated than the young deposit of debris. And in some cases, if the area of hard bedrock is not eroding as much, you can get more soil developed on top of it, which would also make it a little bit softer. And you can see that some of these older sediments are more consolidated than the younger ones. And the absolute worst place to be on this map would be right here on the coastal plain. You can see what happens to the seismic wave. Very low amplitude and wavelength. And then when it hits this, the wavelength shortens and the amplitude increases. It goes back to a short wavelength and then goes to this again. And then as it encounters less rigid units, you can see that the seismic wave, even though the earthquake could have been here, this area would not be near as damaged as this area right here because of this amplification effect. So we've been using what's called VS30, which is the velocity of shear waves in the upper 30 meters of the earth. We've been measuring those throughout eastern Indonesia and in western Indonesia. The way we do it is we put these geophones, like microphones, essentially. We put them into the ground. You can see this, they're all aligned right here in this view. We hook it up to a seismograph. You can see the seismograph right there. And then we hook a hammer that has a sensor on it. We hit the strike plate, which is what Abby's doing right here. There's the strike plate. It sends a seismic wave through this zone. The longer the array, the deeper that you can sense the seismic velocity. So if it goes slow, that means, you have values of 150 meters per second or so. Fast would be 500 to 600 meters per second. The slower it goes, the more amplification you have. So here's the results of our VS30 work in the Banda Islands. You can see that there's very low numbers here in Banda Neira, which is not surprising because the historical accounts tell us that the area at least 5 times in the past was flattened to a rubble heap. You can also see the same problem here on Banda Besar, where the coastal plain is not only vulnerable for a tsunami, but also for damage from ground shaking, even if the earthquake is far away. Like in 1629, when the earthquake was over in north of Ceram, and in 1852 when it was in southern part of Ceram, but the buildings here were completely destroyed. We've also done this on Ambon Island, and you can see the same thing. The coastal plains are the areas where you have the lowest shear wave velocities, which means more amplification effect. And this shows that the area right here where the new bridge is in Ambon, and where the University Patimura is, and where most of Ambon City are very, very vulnerable. We also found an earthquake that happened in Ambon in 1898, and using all of the descriptions we got from each of these points you can see here, it shows that earthquake, the greatest ground motion, was in the places where we measured the slowest velocities. There was also an earthquake in 2019. The earthquake was over here. The earthquake was over here in Ceram, but you can see that the greatest amount of damage occurred right here, where you have this low, unconsolidated bay-fill coastal plain. We also use an instrument that helps us understand the resonant frequency of the earthquake compared to the buildings, and the resonant frequencies of the earthquakes that hit here favor very little damage to 1 to 2 story buildings, but the most damage to buildings that are over 5 stories. This is the new hospital in Ambon right here. You can see no damage here at all from that event, although they're built on the same substrate. But when you look at the hospital, you can see cracks everywhere, especially in the corners, radiating from any kind of corner. And so what it shows is that this hospital has been compromised by a small earthquake in Saram. What about what's going to happen now that it's not structurally sound when another one of those? Fortunately, it didn't collapse because the earthquake wasn't very large, but a larger event or a closer event could cause lots of destruction. So what about the 19 November 2022 earthquake in Chianger? Just happened a few days ago. And you can see total collapse of many buildings. Is there a precedent for this? Yes. We found a journal, a Dutch journal called Physicists Association of East Indies, that documents many of these earthquakes from about 1860 to the early 18th century, early 20th century, and it details many different observations from different points, again using human seismometers. And in March 28th, 1879, in Chianger, we had county buildings that were badly damaged. We had salt warehouse and firehouse, telegraph office, all collapsed. European and Chinese houses collapsed, usually better built compared to the country buildings. Stone bridges suffered. One tore apart. The Mercalli intensity scale was between 8 and 9. And that's exactly what happened a few days ago. There's the 1879 event right there. There was also an event in 1854 right here, which would cause even more damage because it's sitting right on top of Bogor. This is the 2022 map showing, again, Mercalli intensity scales here of 8 to 9, and less as you go away. This looks like a recurrence of the 1879 event. So this fault zone has a recurrence, or could have a recurrence interval of about 150 years or so. What about the recurrence of this one right here? Since this earthquake has happened, it's transferred stress to this area here, which could affect the normal earthquake cycle on that fault zone, which has to be there because it had an earthquake in 1854, right? And what happens when that goes again? Look at the density and population. This is the population density now. And when we made this slide, when we did this research about 5 years ago, we were warning the people in Chianjar about a possible recurrence. Now we need to go here in Bogor in South Jakarta. I can't imagine what's going to happen when that fault zone creates another earthquake. So what do you do about it? Well, if the buildings that are built there, like in Chianjar, are not built to seismic code, then what you have to do is make sure you give a little bit of warning so people can get out of the building. This is an example, the earthquake in Lombok in 2018. This is a school, and you can fortunately no kids were in the school because it happened in the evening. But this whole ceiling here, which is made up of concrete, collapsed. Now, if the students didn't have time to get out and they ducked and covered and held on, you could see that if they ducked underneath their desks, they would have been saved. But the best way is if there's a little bit more distance between the epicenter of the earthquake and where these schools are. There's these earthquake alarms that will sense the P wave of the seismic event, and the P wave will move that pendulum there and touch a sensor and make a sound. And you can have several seconds of warning, in some cases 20 or 30 seconds of warning to get everybody out. These things need to be considered until we can transition into more seismically safe buildings. So the purpose of disaster mitigation is to narrow this gap between what the people in harm's way and what the scientists who have been studying the hazards know. And the three major questions that we need to address are assessing the risk, communicating the risk, and implementing risk reduction strategies. The most important of those three is implementing risk reduction strategies, not making sure that we have assessed it right. Most cases we get an A or a B in this first one, and we fail in these other two. That needs to change. Thank you very much for your time and for all of your support, and may your risk reduction activities be effective. Thank you.